Hi everyone. Can you all hear me? Okay, great. So that means we can start now. So hi everyone, last day of the year, and we are going to learn something really important on the last day of the year. But before that, I just want to know how many of you spent some time on your Renaissance dashboard yesterday? I'm just trying to get a hang of how many of you actually get time to do so. You can just type yes if you could do that. And can you also mention what did you learn? What videos or what assignments did you go through? Fibonacci with all three approaches. Okay, very good. Anyone else who did anything other than that? DP, everything. That's awesome. Okay. LCS variation. Okay, great. Cool. So yesterday we ended our lecture by talking a bit about LCS. So we learned how to write recursive code to compute LCS of two strings, and then I asked you to go back and watch the video on dashboard which memoizes that code. So were you able to understand how the code was memoized using our 2D matrix? Just in case if you have not done that, please make sure to do that today. LCS is a very important question, and it has almost I would say 50-60 different variations, and you never know which of those variations could be asked in an interview. Cool, let's move on. So yeah, once again we are going to solve some very classic problems in dynamic programming. So the problem that we are going to solve now, this is very well known as point change. And once again, each problem in DP can be thought of as a concept. Now in interview, you might not directly be asked that concept. You'd be asked a question, a totally unseen question, where you have to figure out how to apply that concept. Okay, so for that, our understanding of the concept should be rock solid. Okay, so this question goes as follows. It says that we have been given coins of several denominations. So what is the meaning of denomination? Like in India, if you take a look, the coin denominations are 1 rupee coin, 2 rupee coin. You don't have a 3 rupee coin, you don't have a 4 rupee coin, but then you have a 5 rupee coin, and then you have a 10 rupee coin, and then I think you also have a 20 rupee coin. So that's how the denominations work in different countries. So there are different denominations, and they are given to you in form of an array. So let's say the name of the array is coins. The size of the array is m. It means there are m denominations. Okay, and those denominations are, let's say, C0, C1 till Cm minus 1. Okay, now we have been given this array as an input, and we have also been given an integer n as an input, right? Now you can assume one thing. You can assume that we have infinite supply of each denomination. When I say infinite supply of each denomination, let's say there is a denomination of 3 rupee coin, then there are infinite coins of 3 rupee. Okay, you can assume that. Now what we have to do is, given this integer n, we want to find minimum number of coins needed to make n. What is the minimum number of coins needed to make n, as in what is the minimum number of coins which you can collect such that their sum is equals to n. And this array has been given to you, which represents the denominations that you have, and for each denomination infinite coins are there. So from each denomination, you can take as many coins as possible. Is the question making sense to everyone? How many of you get that? Okay, want an example? So let's take some example. Let's say the denominations array that we have has 1, 5, and 7. Okay, so we have got infinite coins of 1 rupee, 5 rupee, and 7 rupee. And now the value of n is 9. So tell me, what is the minimum number of coins that you need to make 9? Okay, so a lot of you are saying 3. Can you also tell me what are those 3 coins which you are taking to make 9? Yeah, 7, 1, 1. So you can take a 7 rupee coin and you can take 2 units of 1 rupee coin. And if you sum them up, you will get 9. Okay. So, you know, this problem is so classic that it is used by certain cash vending machines also. For example, you go to an ATM and let's say you want to withdraw some amount, then the ATM might try to dispense as less notes as possible. Okay. So the ATM might try to dispense as less notes as possible, and also the sum of those notes should be equal to the amount that you have entered. So this can be modeled as a real life problem. Do you see what I'm saying? Yes or no? Yeah. Okay. So tell me, how can I solve this problem? Any basic approach? Same as string type. I do not understand what you're trying to say. So maybe if you elaborate, it will be helpful. Anyone else? Okay, Suraj is saying 2 options for every coin. I think he might be trying to say that for every coin, we can either take it or not take it. But tell me one thing, guys. Let's say this is a very important point to understand now. Okay, so one of you is saying we have 2 options for each coin. Those 2 options, if those 2 options, let's say we assume are either take a coin or do not take a coin, then does it make sense? Let's say you talk about 1 rupee coin. When you talk about 1 rupee coin, either I can leave it completely, or I can take it once, or I can take it twice, or I can take it thrice, or I can take it 4 times. Why? Because there are infinite supply of each denomination. It's not like you have got 1 unit coin of each denomination. No, it's not like that. There are infinite supply of each denomination. So whenever you are scanning this array and let's say you are considering this element, then there are several choices for this element. First choice could be do not take it at all and then move on. Second choice could be take it once. Third choice could be take it twice. Do you see what I'm trying to say? Yes or no? Right? Yeah. So this is not as simple as take and leave problem. Do you remember yesterday we solved a take and leave problem where we had to maximize the sum of non-adjacent elements? How many of you remember that? In that question, for every element, we had only 2 choices. So either you take it and move on, or you leave it and move on. Do you understand? Yes or no? And when you take it only once. But in this case, that is not true, because here, given an element, you can take it as many times as you want. And you can leave it also. If you want, you can leave it. Like in this example, n equals to 9, you left 5. You took 7 once and you took 1 twice. Understanding the difference between this and the last question. So, you know, whenever such assumptions are part of some question, then they lead to changes in the approach. And that is exactly what, as a good problem solver, you have to detect. Okay. So there is a very well-known approach to this problem, which a lot of people come up with. I'm not sure why none of you is coming up with. That is kind of a greedy approach. Anyone who has some greedy approach in his mind? Yeah, Abhijit is saying first we will take the closest element of n. Very good. So that is the approach which a lot of people come up with. How many of you agree with him or at least understand what he's trying to say? Okay, let's take a look. So what Abhijit is trying to say is you want to make 9, okay? Now assume that this array is sorted for now. Let's make that assumption. So start from the end. When I say start from the end, try to take the largest denomination, because when you take the largest denomination, then n decreases very fast, right? And that is what you want. You want that by taking fewest possible coins, the n should have decreased to 0. That is what you want. So he's saying first take this 7. So okay, I took this 7. When I took this 7, the remaining amount becomes 9 minus 7, which is 2. Now you cannot take this 7 again. So you can move back to this 5. When you come to this 5, can you take this 5 for n equals to 2? Does it make sense? Yes or no? The answer is no. So again, you will move back. Now you come to this 1 and you want to make 2 rupee. So you have to take 1 rupee coin twice. That is what you do. And now it becomes 0. So this is the approach that a lot of people come up with. It start from the end and take the current coin as many times as it is possible to take, and then reduce your n, and then again take as many times as possible. This is how you keep going on. Is it making sense what this approach is? Whether it is right or wrong, we'll come to that later, but makes sense. Now a lot of you are saying it will fail. So a lot of you are saying it will fail for other kinds of input like n equals to 10. So tell me clearly, whatever algorithm I told just now, if I run it for n equals to 10, then how many coins would be taken? 4 coins. And what are those 4 coins? 7,111. Exactly. So again, you start from the end. You see that this 7 can be taken. So you take this 7, right? And now the value of n becomes 3. Can you take it again? No. So you'll move back. How about this 5? Can you take this 5 again? Or can you take this 5 at all? The answer is no, because this is 3 already. So again, you move back. Now you are here. So you'll take that 1 for 3 times. So you have gathered 4 coins. But think and say, what is the fewest number of coins that can make n equals to 10? Given this denomination, it is 2. I can just take 5 followed by another 5. So the algorithm that we just discussed, which is greedy in nature, which always takes the highest denomination and then moves back, that is not going to work. Does it make sense to everyone? Why is it not going to work? Typing yes or no. Yeah. Okay. Cool. So let's move on and scrap this approach and come up with a smarter approach. So tell me, what can be done? How do we think? So don't think about DP, don't think about anything which is very, very Herculean to think of. Think of a simple recursive way. See, whenever you see questions like find minimum, find maximum, then automatically that question has a high probability of being solved using DP, right? I mean, certain times DP might not be necessary. Certain times it can be solved using simple logic like greedy. Certain times it can be solved using binary search, which will teach you. But chances are very high that it is DP. If it is DP, the first step is recursion. So think recursively. One of you is saying pick, answer, stay or leave. Okay. Okay, so Satish is saying we can check all possible ways and find min. Yeah, that is too easy to say, but if you go ahead to find all possible ways, that itself could be a challenging problem. It can be done using recursion, but it could be a good problem to solve. You know, here if you focus on this problem, here you don't have to tell me which coins did you pick. Like for n equals to 9, you don't have to tell me, hey, I picked 1 7 rupee coin and 2 1 rupee coin. You don't have to tell me that. You just have to tell me the answer 3, that 3 is the minimum number of coins that I picked. So if you focus on this and work your way out, you might be able to come up with a very easy recursive relation, and let us understand that. So let's keep looking. See, let's say you want to make n rupees, okay? And this is the array that you have. Okay, well, let me write a new array. This is the array that you have of size m. So that's your array starting from I equals to 0 to m minus 1. And then there are certain elements in this. Tell me, like, if you want to make n rupees, then in how many different ways can you choose your first coin? In how many different ways can you choose your first coin? If there are m options over here, in how many different ways you can choose your first coin? Tell me. In m different ways, right? See, you have got 1 rupee coin, 5 rupee coin, 7 rupee coin. So what is the in how many different ways can you pick your first coin? It could either be 1 or 5 or 7. So it depends upon the size of the array. So there are m options that I have for my very first coin. Is that making sense to everyone? Yeah. Okay. Now just think of it. If you have taken your first coin as this, which is array 0. So you wanted to make n rupee coin, and if you take your first coin as array 0, then how much amount will be left? How much amount will be left? You wanted to make n and you took array 0. So now the amount left will be n minus array 0. Let me just write it as a. Okay, but you could have taken other decision also. That other decision could have been to take this as your first coin. If you would have taken this as your first coin, which is a1, then the remaining amount would have been n minus a1. Similarly, you can see there would be so many options. The final option would have been to take the last element. If you would have taken the last element, which is a of m minus 1, then the remaining amount would have been n minus a of m minus 1. So these are the transitions that are possible. So you can think that this is a state and you move from this state to this state if you pick this as your first coin. But if you pick this as your first coin, you move from here to here. Similarly, if you pick this as the first coin, you move from here to there. Do you understand how these transitions are being made? Yes or no? Yeah, others, yes, no, too hard to understand, too easy to understand, what? Too easy to understand, right? Okay. Now tell me one thing. So when you have made a decision to pick this coin or that coin or whatever as your first coin, then you have already picked one coin. Because you have already picked one coin, you should do 1 plus something. Now the question is, what should that something be? So think of it in this manner. You wanted to make n rupees, and after picking one coin, you want to make n minus a0 rupees. Now, if somebody tells you what is the minimum number of coins that is required to make this much rupees, and what is the minimum number of coins that is required to make this much rupees and then that much rupees, then it looks like your job is done. Now, who is going to tell you? Let's say some magician. Let's say some magician tells you that, hey, the fewest number of coins that you need to make this much rupees is X. The fewest number of coins that you need to make this much rupees is Y. And the fewest number of coins that you need to make this much rupees is Z. Then using those, you can very easily solve for the fewest number of coins used to make n rupees. Is this making sense? Just type in yes or no if you get that. Right? Okay. We can even take a very quick example here, which corresponds to all that I have said. Let's say your array is 3, 4, 7, and your n is 10. So there is a function that you call for the current value of n. Now tell me, how many transitions will happen from here? Look at the size of the oriental. How many choices do you have for the first coin? 3 choices. And what are those 3 choices? Your first coin could either be a 3 rupee coin. If that's your first coin, you will move from f of 10 to f of 10 minus 3, which is 7. If your first coin is this, you will move from f of 10 to f of 10 minus 4, which is 6. And if your first coin is this, you will move to f of 10 minus 7, that is 3. You understand these transitions, how they are happening, right? Now, when you made this choice, then the first coin that you picked was a 3 rupee coin. When you made this choice, then the first coin that you picked was a 4 rupee coin. When you made this choice, then the first coin that you picked was a 7 rupee coin. Now, all that I'm trying to tell you is, let's say there is a magician and he tells you the fewest number of coins required to make remaining amount. That is 7. So tell me, what is the fewest number of coins that you need to make 7 rupees? Given that denomination? 1. Only 1. You can pick that coin and your job will be done. So 2 coins are needed, right? And what is the fewest number of coins needed to make 6 rupees? Given that denomination? 2, right? And what is that? You can pick 3 followed by 3. And what is the fewest number of coins required to make 3? Just 1. Pick that 3. All that I'm saying you is, you realize that for this, the answer is 1. Because you just need 1 coin to make 7 rupees given this denomination. Similarly, for this, the answer is 2. You just need 2 coins. For this, the answer is 1. So if somebody tells you this is 1, this is 2, this is 1, then you can tell me the answer for this. What is the fewest number of coins needed to make 10 rupees? Tell me. Now, what is the fewest number of coins needed to make 10 rupees? It is 2. And how did you get that 2? You got that 2 by doing 1 plus. Why did you do 1 plus? Because the moment you have made first transition, that means you have taken some coin. Which coin, I don't care, but you have taken some coin. Now, whatever is the minimum of this, this, and that, I can add it. So whatever is the minimum of F7, F6, F3, that can be added to 1, and that will be the value of f of 10. Does it now make sense? How many of you understand the idea? If you still need a repetition, you will have to tell me what to repeat. Yeah. Yeah, others? Yes, no. Can we move on? Is that now clear? No, that's the reason learning recursion is very, very important. Those of you who sincerely learned recursion, you will find it very, very intuitive to understand. Yeah. Okay, great. Cool. So does it look like, forget about magician. Why did I say magician? Say there is a function f of 10. I mean, hey, somebody tells you that what is the minimum number of coins that you need to make 7 rupees. Somebody tells you that. Now somebody tells you what is the minimum number of coins needed to make 6 rupees. What is the minimum number of coins needed to make 3 rupees? Somebody tells you that. Okay, here it is 1, here it is 2, here it is 1. So what will be the minimum number of coins needed to make 10 rupees? It will be 1 plus minimum of 1, 2, 1. You see, if you are making 7 rupees by 1 coin, then you can add 3 to it as another coin, and now you have just 2 coins using which you can make 10 rupees. Do you get it now? Yes or no? There's nothing too special about it anyways. Yeah. Okay, so do you see that it is purely a recurrence relation? How many of you are able to note that? Yeah. Okay, and if you want, you can even draw this recursion tree and see how the values are being returned. So this is final chance for others to try and understand who are still wondering what's happening. So let's say f of 10. From here, you will call f of 7, f of 6, and f of 3. This diagram is copy paste of that. Okay. So now what is the meaning of f of x? the meaning of f of x is it will return me fewest number of coins to make x. That is what f of x is. Is that clear? So I'm saying fewest number of coins needed to make 10 rupees is equals to 1 plus minimum of this, that. Why I'm doing 1 plus? Because the moment I made my first choice, I already took 1 coin. It was either 3 rupee coin or 4 rupee coin or 7 rupee coin. Now these are remaining amount. So if somebody tells me what is the minimum number of coins to make those amount, I can take min of those, add 1 to it, and that will be my answer. Okay. So again, you can go on from here. At f of 7, again, there can be 3 transitions, because at every stage, you can pick any of these 3 coins. Why? Because they are in infinite supply. So again, f of 7, can you tell me what will be the functions which will be called by f of 7? Yeah, very easy to say, right? Because once again, I can say that my current coin could either be a 3 rupee or 4 rupee or 7 rupee. So if my current coin is a 3 rupee coin, 7 minus 3 will be 4. If it is a 4 rupee coin, it will be this. And if it is a 7 rupee coin, it will be 0. That's how things are happening. Now again, I hope you remembered the definition of f of x. If you really remember the definition of f of x, can you tell me what should f of 0 return? What is the fewest number of coins that I need to make 0 rupees? Why do you think it should be 1? You don't want to make any money. Why do you need a coin? You don't need a coin. So when n is equals to 0, just return 0. So this can be your termination condition of the code that you will write. Clear? Yes, no? Why we are returning 0 here? Yeah. Okay. Now again, like I can draw more, so you can again see that here again there are 3 choices. So at each node there are 3 choices, or to generalize it, at each node there are m choices, where m is the size of your array, where m is the number of denominations that you have. So once again, at f of 4, what will be the calls that you will make? 4 minus 3, which is 1, and 4 minus 4, which is 0. And 4 minus 7, which is minus 3, interestingly. This looks a bit itchy, right? Where the remaining amount is negative. What to do in this case? When the remaining amount is negative, what to do? Okay, some of you are saying return 0, some of you are saying int max, which is infinity. Okay, others? But you realize it that this can happen, right? Certain times the remaining amount can become negative. Why it can become negative? Because you never know what this value is. And when you subtract an element from this, it can become negative. So you have to handle this thing in a proper manner. I'll come to that. But before that, I'll give you a very quick example to solve. So let's say we have denominations of 2, 4, 6, and we want to make 5 rupees. What is the fewest number of coins that I need to make 5 rupees here? Is it possible to make 5 rupees here? Not possible, right? So this is very important thing to realize. Now guys, let me tell you one thing. See, if you look at these edges, these are like your decision arrows. So in this particular arrow, you took a 3 rupee coin. That is the reason you moved from 10 to 7. So I'll draw it here, 3 rupee coin. In this arrow again, you took a 3 rupee coin. That is the reason you moved from 7 to 4. In this arrow, what did you take? You moved from 4 to minus 3. So you took a 7 rupee coin. You know, I would say that this particular decision path is not a correct decision path, because if you are moving along this path, you cannot create the desired amount, which is 10. And furthermore, I can say there is no way I can create negative amount from positive denominations. There is no way I can create negative amount from positive denominations. So this is impossible thing. This is impossible thing. So let me erase these for now. Now, in recursion, what you do is you solve every sub problem one by one. So at f of 4, what you are trying to solve, forget about this big tree, just focus your attention on this small tree. At f of 4, you are trying to find fewest number of coins to make 4. Fewest number of coins to make 4 is dependent upon fewest number of coins to make 1, 0, and -3. Now think, what should this return? What should f of 1 ideally return from here? When you look at f of 1, you realize that, hey, given this denomination, 1 cannot be made. When you look at f of 0, you can say that because of this termination condition, I can return 0 from here. Now, these are the impossible things. So whenever you encounter impossible things, what should ideally be returned? Forget about this for now. Let's focus on this. Some of you, those who are saying return infinite, you are saying totally correct. Why you are saying totally correct? Because whatever is returned from here, you want to discard that. Why you want to discard that? Because it is not possible to make infinite amount. Correct? Now, if you are taking min of certain things, let's say min of 5 comma infinity, it will always be 5. Min of -5 comma infinity, it will always be -5. So when you are taking min of certain things, out of those things, if something is infinite, it will automatically be discarded. So what we can do is, if my function has ever been called on a negative amount, then I'll immediately return infinite from there, because returning infinite will ensure that for the computation of this thing, when min will be taken, then whatever is returned from here will automatically be kicked out. Does it make sense why returning infinite makes sense? Yes or no? Yeah. So this is very, very important point to understand. So certain times you write this kind of relationship, certain times you might write a relationship which says 1 plus max of something, something, something. And in that, if you realize that you end up on a state which is impossible state, and if you're taking max, maybe you can return minus infinite, because max of x comma minus infinite will always be x, correct? So this is again another trick that I want you guys to understand. So, this is how it happens. So our first termination condition is that if the remaining amount is 0, return 0. And it makes sense, because if I go by this definition, this makes sense. Similarly, if my remaining amount is negative, then return infinite. Correct? Okay, now look at this f of 1. What will happen at this f of 1? When you look at this f of 1, again from here, you will make all those 3 calls, which is f of 1 minus 3, which is -2, f of 1 minus 4, which is -3, f of 1 minus 6, 1 minus 7, which is -6. Now all these things will return infinite, infinite, infinite. All these things will return infinite. And now again, from here, you can make sure to return another infinite, because you can just write your code in a way. I'll come to the coding part. You can write your code in a way that 1 plus integer infinite is also an infinite value that is returned to the top. So eventually what will happen from here is, when you take min of this, this, and that, it will turn out to be 0, and f of 4 will be 1 plus 0, which is 1. So you will return 1 from here. And returning 1 makes sense, because if somebody asks you a question that what is the fewest number of coins needed to make 4, you would say 1, just take this thing. Similarly, in this manner, calls will go down, down, and down, and values will be returned. And that is how you can now imagine something will be returned from here, here, here. And f of 10, what it will do is, it will find min of those, add 1 to it, and that will be the answer of f of 10. Okay, does it make sense now? How many of you follow the approach well? Yeah. Any questions, then feel free to ask before we code this exact approach. How many of you can write the recursive code on your own for this thing? Okay, then what are we waiting for? Let's write it. So So write, if you want to write a pseudocode, write that as well. Just you can put it in the chat box once you are done writing. Everyone should at least try. Yeah, this is your final lecture on dynamic programming. Okay, let's look at the recursive code for this. Let's say there is a function called as mincoins. This function returns something. What does it return? It returns the minimum amount needed to make n rupees. Okay, so you pass here n, correct? Now, tell me, what is the first line of code that I should have? What is the first line of code that we always have been having since last 3-4 classes? Base case, right? And what is the base case here? There are two base cases here. First, when n is 0, we return 0. And there is one more base case we just learned. If remaining amount is negative, then in order to discard the contribution of that, because we are taking min, we will return infinite, which depending on your language, you have to see, like in C, C++, there is a provision of int_max, which is the largest value that an integer data type possesses. Okay. Otherwise, what to do? So now comes the logic, which should be as simple as this. So whenever you are at a particular function call, let's say you are at f of n, you should be making all these calls. And how many calls will be there? Tell me. The number of calls will be equal to m, because that is the number of denominations that you have. So do I need a for loop here? I need a for loop, then only I can make those m calls, right? So I'll iterate on my coins array. So for I equals to 0, I smaller than m, I plus plus. So see, what this for loop is doing is, if this is my coins array, then my I is moving on from 0 to m minus 1. So let's say currently if my I is here, then I want to take this coin as my current coin. Now, when you take this coin as your current coin and present amount was this, then what will be the leftover amount? You take a of I and the present amount is n, then the leftover amount will be n minus a of I. I had shown it to you, right? So I can say the remaining amount will be n minus ai, correct? And you will make a function call on this. So you will call mincoins method on this, correct? And also because you have taken this ai currently, so you have to add +1 to it. You add this +1 before, after, does not really matter. Okay, and you want to do this thing for all the values of I. That is the reason you have written this for loop. You want to do this for all the values of I, and for whichever value of I you are getting the minimum possible value of this, that will lead to your answer. So what I can do is, before starting this for loop, I can have an answer variable, and I can initialize this answer to infinity. Let's say it is int_max to start with. And now every time what I'll do is I'll update my answer. I'll write answer equals to minimum of this expression, comma, answer. So all that is happening is, think of it in this manner. You made this call, okay? You made this call and it returned you, let's say x. It returned you x. So you have 1 plus x with you, and your answer was initially infinity. So you update your answer to min of this, comma, that. And then you make this call, and then whatever is returned, using that, again, you update your answer. So this is just like, scanning 10 different values or m different values and finding out their minimum. So I have initialized answer to int_max, and every time I'm making the call, adding one to it and updating my answer if possible. Is it making sense, this piece of code? Just type in yes or no. Yeah, others? Yes, no? Yeah, I'll come to the remaining part, but do you understand why that for loop is there and everything? And you understand why that for loop runs from I equals to 0 to m-1, because there are m denominations. Okay, now once this for loop would have been over, then think of it in this way. From this function, you would have made all these calls and you would have gotten your actual answer. So what are you waiting for? You can just return this answer. That's it. Clear now? Okay, now there is one very good question that a lot of you are asking. See, I had told you in situations like these, like at f of 1, it might happen that all the children are returning infinite, infinite, infinite. So if you compute 1 plus min of int min, and store it in an integer, let's say x, what will happen? How will your computer respond to this? Theoretically, you will say, hey, 1 plus infinity is infinity, but your computer will not agree to it, because if you add 1 to maximum integer value, sorry, minimum integer value, it's not maximum, sorry, it's max, not min, max. So if you add 1 to the maximum integer value, it will lead to overflow. So there is an overflow scenario that can happen over here. Is it making sense to everyone? Yeah. So this is a very, very important point to understand. So how to handle that? All that you can do is you can change the types to long. So if you change the types to long, 1 plus int_max, whatever it will still be greater than integer infinity, but it can be accommodated in a long. So in questions like these, this is also another point of care that you have to take in your mind. Does it make sense, this point, why we need a long over here? Yes or no? There has to be some response. Either you got it or you did not get it. Yes, no. So that we move on. Yeah. Okay. If you don't get it, then maybe learn about what an integer flow is. These are some very basic concepts. I have talked about it in the module 0 as well. It's good to know about those things before you write some code that's based on it. Okay. Cool. Anyways, so tell me one thing. Now, this is the code that we have, and this is the recursion tree diagram that we have. So here, n is something which defines our state. And what is n? It is the remaining amount. Now tell me something. Do you see overlapping subproblems over here? How many of you can see that? So can you pinpoint any one overlapping subproblem? Yeah, 3, 3. So you can say, you can easily see that this f of 3 is present here also and here also. Overlapping subproblem is happening. So how do we counter overlapping subproblem? Memoization. Very good. The first step you guys have figured out. Those of you who are actually watching your dashboard, you will grow very fast as compared to others, because here you see things happening, and on the dashboard you will find things very, very relatable, and then it will be super easy for you to solve questions in the future. So yeah, the first thing I'll do is I'll create a memoization array. Now, what should be the dimension of this? Is this a one-dimensional problem or a two-dimensional problem? It's one-dimensional problem only. Why? Because the problem is being denoted only by one integer. The remaining amount is just one integer. It is not 2 or 3 or 4 integers. Okay. So I need a one-dimensional memoization array. And what should be the size of that array? So if you take a look, the value n will keep on reducing only. Why? Because you are always subtracting something from it. So the different values of remaining amounts that you will see in this tree, or the different values of this integer that you will see at the nodes of this tree, will be smaller than or equals to n. Now from 0 to n, there are n plus 1 integers, so it's good to initialize it to that, right? And you can initialize all of them to some value like -1, -1, -1. Why? Because I know for sure that the fewest number of coins will never be -1. Can it ever happen that number of coins is -1? No. So I can initialize everything to -1. And now you just need to write your memoization logic over here, which is, I think, super easy thing to do. How many of you can memorize this code now, given the code already and the memoization code already? So tell me, what is the first step of memoization? Base case remains as it is. No one is going to touch that. Okay. Now, after base case, the first thing that you will do is you will check in the memoization array whether answer for n is present or not. So after this line, you can write if, I hope this part is visible. You can write if mem of n not equals to -1. Okay. So what I have written is if mem of n not equals to -1, then you can just return mem of n, right? Otherwise, what you can do is you have computed actual answer in this case, because if let's say you had not solved for the amount n, then you have solved for it. And after solving for it, first store that answer in mem of n, and then go ahead and return that answer. So everything is still the same. The first part is mem check. The second part is solve and then store and then return. That's it. Is the code clear to everyone here? Yes or no? Yeah. Okay, cool. Now again, what is the time complexity of this? Let's come to the actual time complexity later, but do you somehow realize inside that this code will be much more optimal than the previous code? Because if you have solved for f of 3 here, if you have created a just gigantic tree for f of 3 here, you will not create that here again. It will for sure be more optimal. Now, how optimal? What will be the time complexity? That is again your homework. Go back, watch your dashboard. There again, it is very well explained that how to calculate the time complexities of such recursion plus memoization. Cool. Any questions in this so far to anyone? No questions? Great. Okay. We will take another plunge in the same problem. I had told you that there are different variations of this problem. So let us quickly take a look at second variation. So now you have been given, again, the same thing. You have been given the coins of some denominations, okay? And you have been given an integer n, okay? Now what you have to do is you have to find number of ways to make n. This question is different. In the last question, we were interested in finding what is the minimum number of coins to make n. Here we are interested in knowing then what are the different ways in which I can make n. Do you understand the difference between this and the last question? How many of you do? Just type in yes or no. Yeah. Let's take a quick example. We have 1, 2, and 3, and n is 4. Will tell me the answer. How many different ways are there? It will be great if you also list down those ways. The question is that you have been given n, which denotes the amount which you have to make, and you have the same array that you had in the last question, and you have to tell me how many different ways are there in which I can make n rupees. Okay, let's take a look. I have got infinite supply of each of these coins. So what I can do is I can take 4 units of 1 rupee coin. So I can take 1, 1, 1, 1. That's it. Another way could have been I take 2 units of this and 1 unit of that. This sum is also 4. Another way could have been I take 2 units of this. And one more way could have been 1 unit of this and that. Is it clear how these are the 4 different ways here? Each of them is different from the other. Yeah. Okay. Now some of you are asking me this question: is 112 different from 211? What do you think? Should both of them be considered same or different? They should be considered same, because here also the combination of coins is that you have 2 coins of 1 rupee and 1 coin of 2 rupee, and here also the situation is same. Just by jumbling up the order, you can't say that it is different. In order to be different, there has to be difference of some element. Like here, I can say that it is missing out on ones and so on and on, right? Is the question now absolutely clear to all? Yes, no? Yeah? Okay, awesome, great. So let's move on. Tell me, how can I approach this question? Okay, so one of you is giving a very interesting idea. Then Shivam is saying instead of finding min, we have to add up all the combinations. Anyone else who agrees with him? He's saying that previously we were taking min of the function calls, and now we should probably add the result of those function calls. Okay, one of you seem to agree with that. Anyone else? Okay, it's a very interesting approach, and we will understand why this is right or why that is wrong whatsoever. Let's talk about it. So let me first tell you the approach. Everyone look at the board now. Let's say the amount is n. Okay. Now, how many choices do I have for my current coin? 3 choices. And if you take those 3 choices one after the other, then what will be the new states that you will move on to? So if you take 1, you will move on to n minus 1. If you take 2, you will move on to n minus 2. If you take 3, you will move on to n minus 3. So this is something which all of us understand now. Now the approach that one of you is giving is, you're saying that, hey, if you know number of ways to make n minus 1, number of ways to make n minus 2, and number of ways to make n minus 3, you can just add them up, and that will give you the number of ways to make n. So you are saying that number of ways to make n is simply the sum of everything else that it calls. This is what some of you are saying. Is it making sense to everyone? Whether it is right or wrong will come later, but is it making sense where from this equation came? Now, what do you guys think? Is this equation correct? Will it give us the right answer? 2 of you are saying no, and 1 of you has already realized why it is no, because I think Shivam, you're saying it will lead to duplicates. Very good. Will it lead to duplicates? Let me ask you this question again. What is the meaning of duplicate? Like if you have considered 1, 3, you should not consider 3, 1 again. That is not allowed. Both are the same. Okay. See, let me tell you one thing. Here you are saying that in this transition, the first coin that you have with you is 1, right? And then you don't know what sort of coins are used to make the remaining amount. So here your n was 4, and from 4 you move to 3. and here you move to 2, and here you move to 1. So in this transition, the first coin you took was 1 rupee coin. In this transition, the first coin was 2 rupee coin. In this transition, the first coin was 3 rupee coin. Now just think and tell me. In this transition, the first coin is a 1, here it is 2, and here it is 3. Now, the remaining amount is 3, and you can make this remaining amount 3 by taking a 3 rupee coin, right? So from this path, you will get 1, 3 as a particular possibility. But when you look at this path, a way to make 1 rupee coin is to take this thing, and then you will create 3, 1. So you will get a combo of 1, 3 from this path, and you will get a combo of 3, 1 from that path. Can you note this thing? Yes or no? Right? And will it not lead to repetition then? The answer is yes. So this is not the right way. Why? Because of the duplicates that it will bring in. If you add up these things, some combination which was present over here, that combination could have been x, y, z, can again be present over here in the form of z, y, x. And this is something that I don't want. Others, sensible enough? Yes or no? Is this point? It's very, very important to understand that why a particular relation is right or a particular relation is wrong. Otherwise, anyone gives you any relation and throws some logic at you, you'll always feel it is right. Okay, but you have to deep dive and explore if it is wrong, why it is wrong. Anyways, so this approach is not going to work. So what to do now? Think of it. So guys, if you carefully look here, the problem is happening because at each stage you have m choices. Because at each stage you have m choices, so it might happen that from somewhere you picked 1, 3, and from somewhere else you picked 3, 1, right? So how about making sure that at each stage we do not have equal number of choices? How to make sure of that thing? So I'll tell you a bit about it. Let's talk of it. So this approach that we are going to learn now is super powerful, has extensive application, and is very important to understand. Okay, see, think of it in this manner. This is your array, and this is the amount that you need to make. Okay, so visited array and all, no, not needed. This is not a graph problem. You don't have cycles here. Okay, let's talk about it in very basic terms. We want to make this much amount, 4 rupees. Let's write it here. Now what you can do is you can start your journey from the first element, or you can start your journey from the last element. It is up to you. So let's say I start my journey from the last element for now, which is at index number 2. See, this is your index 0, this is index 1, this is index 2. So let's say you start from index number 2. Now tell me just one thing. When you are at this element, then how many choices do you have? Can I say I just have 2 choices? Either I can take this element once, or I can just leave it. Is it right to say that we just have 2 choices of this category? The answer is no. See, either you can leave it, or you can take it once, or you can take it twice, or you can take it thrice, because there are infinite supply. Okay, so the first choice that you can tell me is where you decide to leave this thing, where you decide to leave this element at index 2. So if you leave this thing, what will happen is, will your amount change? Your amount will not change. If you are leaving this, your amount will continue to be what it was. And now because you are leaving it, so it makes sense to move back. Moving back means coming from index 2 to index 1. So this is your leave transition. Is it making sense to everyone? Whenever you leave an element, you come from index I to index I minus 1, and your amount stays the same. Correct? Okay. On the other hand, if you take it, if you decide to take this element, then what will be the remaining amount? The remaining amount will be 4 minus 3, which is 1. So let's write it. The remaining amount will be 1. But does it make sense to move back? Does it make sense to move back? The answer is no, it does not make sense to move back, because the moment you move back from here, you won't be able to take this thing again. So in this case, what we'll do is, whenever we take something, then we stay there. We stay there. So the index will not change. And why we are doing it? Because in the future, we might want to take it again. You see my point? So if you are leaving something, reduce your amount. Do not reduce your amount, because you're not taking it at all, and decrease your index. But if you're taking something, then reduce your amount, but do not change your index. So this is a very different kind of transition, but yeah, this is how it is. Is it making sense that why we are not going back when we are taking something? Yes or no? Okay, great. Now I have a very simple problem for you. Let me define a function. Okay, here there are two items that you have. So the first item is an index, and the second item is remaining amount. Okay, this index denotes that the part of the array that I am working in is from 0 to idx, and this remaining amount is just remaining amount. Now f of idx tells me that in how many different ways, listen to it very, very carefully. F of idx comma remaining tells me that in how many different ways can I create this amount from this much array. So let me write it. In how many different ways are there to make remaining amount from the part of the array which is from 0 to idx. So you don't have to consider the denominations beyond idx because you left them. This is how I am defining this thing. Is the definition making sense? Just type in yes or no. Right? So you can take a quick example. What should be the value of f of 1 comma 4? Tell me. Okay, some of you are saying 3, some of you are saying 2. Can you tell me what are those 3 ways, or what are those 2 ways? Yeah. So guys, if you see here, the meaning of f of 1 comma 4 is different ways to make 4 from the remaining array, which is from index 0 to 1, from here 0 to 1. From 0 to 1 you have got 1 comma 2. So you want to make 4 rupees from this much of array. How many different ways are there? Tell me. There are 3 different ways. First way is you take this 1 for 4 times, and second way is you take this 1 for 2 times and 2 for 1 time, and the final way is you take this 2 for 2 times. So that is the meaning of f of idx comma remaining amount. Do you get it now? Yes or no? Yeah. Okay. Now can you tell me what will be the value of f of 2 comma 1? F of 2 comma 1, what does it mean? It means different ways to make 1 rupee, right, from the part of the array which is from 0 to 2. The part of the array which is from 0 to 2 is 1, 2, 3. So in how many different ways you can make 1 rupee from the given array? There is only one way, which is by picking that 1 coin. Okay, good. Now, if you have really understood the meaning of f of idx comma remaining, let me come to the point now. See, when you made this transition, then you rejected this element completely. When you rejected this element completely means all the combinations of coins that you will get over here will definitely not contain this element, which is array of 2, right? Because you left it and move ahead. So all the combinations here will be those which will not contain this item in it. Is this intuitive enough to understand? Yes or no? Right? And when you made this transition, then all the combinations in this will be that which will definitely contain the last element, which is array 2. So this is that combination which will definitely not contain this, and this is that combination which will definitely contain that, because this is for leave and that is for take. Is it making sense to all that how there will be no intersection between these two sets that you are going to get? Okay, great. Now I can say that, hey, all the combinations that I get from here and all the combinations that I get from here will correspond to my overall answer. Why to overall answer? Because see, all the combinations that you get from here, f of 2 comma 1, what is f of 2 comma 1? F of 2 comma 1, we realized it is 1 only, because there is only one way to make 1 from this much part, which is take a 1 rupee coin. And if you concatenate your take transition to it, where you took this 3, then you can say, yeah, from here I am getting one way in which I can make 4 rupees from the entire array, correct? And from here, what was the value of f of 1 comma 4? It was 3. There were 3 different ways. So there were 3 different ways from here, and there was 1 different way from here. So total number of ways will be 3 plus 1, that is 4. Okay, so this way is that in which the last element is not included, but still the amount that you are making is equal to n. And this way is that in which the last element is included for sure, and the amount that you are making is again n. So whatever this function returns and this function returns, you add them up and that will be your eventual answer. Does it make sense? How many of you get that? So that's all about it. Now, if you go ahead, you can just draw this diagram on and on. So again here, tell me, at every index, you have got 2 choices, leave or take, correct? So what is your current index? Current index is 1. At index 1, you have got a value 2, right? So if you leave this element, if you don't decide to take this element, will the remaining amount change? The remaining amount won't change, but you will move back, because in leave transition, our index always reduces. So you will come from index 1 to index 0. Okay, what will be the state in take transition? Can you tell me? Others, can you make some efforts? What do you do whenever you take an element? Whenever you take an element, then the remaining amount decreases and your index does not change. It stays the same. Okay, good. Very good. That's the right answer. So if you take the element at index 1, which is 2, then the remaining amount will be 4 minus 2, which is 2. And you will stay at the same index, which is at index 1. Cool. This is how you can again move on. So again, you are at 0, 4. So again, there are 2 possibilities, which is of leave or take. So at index 0, you have got 1. So if you do not take this, your remaining amount stays the same, and you move on 1 index back, which is -1. And if you take the element at index 0, which is 1, then your remaining amount becomes 3. Okay, and you stay at the same place, which is 0. Now again, calls will keep getting made from here, so on and on and on. Now we need to think about termination condition. What to do in this scenario? Here the index became negative. The index became -1. What is the meaning of index becoming -1 according to you? No coins. Very good. You're coming back. You're coming back. The moment your index became -1, that means there are no coins that are left. So the physical meaning of this situation is that, hey, you don't have any coins with you. You have 0 denominations with you, and you want to make 4 rupees. Tell me, is there any way to make 4 rupees when we have no denominations with us? The answer is no. So if my index is negative, right? I'm just writing that rule. If my index became negative and the remaining amount is still positive, then there are no ways. So in this situation, we should return 0. Is that clear? Yes or no? Right? This is very important. But now think and tell me, what if this remaining amount was 0? Somebody tells you that, hey, you don't have any denominations. Now tell me how many ways are there to make 0 rupees. You'd say only one way. Yes, only one way. And that one way is an empty set. You don't pick anything, an empty set. So if your I is negative and the remaining amount is 0, then there is only one way to make that. In fact, there is an interesting thing. You can see one thing for sure, that this thing is also reducing and this thing is also reducing. In all the calls that you are making, your index and remaining amount both are reducing only. It is never so happening that they are increasing. So use your brain and tell me one thing. Let's say your index is equals to 5 at any point of time. That means you will consider this much part of the array from 0 to 5. And your remaining amount is 0. So somebody tells you that, hey, in how many ways you can make 0 rupees if you have this much of denomination? What will be your answer? In how many different ways you can make 0 rupees? 0 is not the right to say. Your answer should be 1, because if you want to make 0 rupees, no matter what denomination you have or not have, you can always create an empty combination. You can always create an empty combination, and there is only one empty combination. So I can say, if my remaining amount is 0, I'll directly return 1. Why? Because no matter how many denominations I have, there is one and only one way to make 0 rupees, which is take empty combination. And I can take empty combination at any point of time without knowing what denominations I have. Is it making sense to everyone that why return 1 when remaining amount is 0? Yes, no? Yeah, okay. So that will be probably our first important termination condition. The moment remaining amount is 0, just return 1. There is only one way for that. Okay. And what to do if remaining amount is negative? You realize that certain times remaining amount can become negative also, right? Because think of it in this way. Let's say you wanted to make 4 rupees and this was 5. So if you would have taken it from 4, it would have become -1. So is there any way in which you can make a negative amount from positive combinations, from positive denominations? Can you make negative amount from positive denominations? The answer is a big no. So if the remaining amount is negative, just return 0. So these two termination conditions have to be there because my remaining amount is reducing. But another thing to be noted here is that your I, which is index, is also reducing. So you need to have one termination condition for your index also. If my index becomes negative, tell me, if my index becomes negative, and the way I have written my termination conditions is, this is my first, this is my second, this is my third. So you will come to this if only if these two conditions were false. If these two conditions were false, it automatically means that remaining amount must have been positive, isn't it? See, if an integer is neither 0 nor negative, that means that integer is positive. So if you come to this if condition, it means that your remaining amount is positive, but you are out of coins. Why you are out of coins? Because your I is negative. So in this situation, what to do? In this situation also you return 0 because you have nothing with you. You have empty denominations with you and you want to make a positive amount. There is no way you can make that. So these are the 3 different termination conditions that I would need to have. Is that clear? How many of you understood the point? Okay, can code this approach? Let's talk about the code. What do you think? What is the dimension of this DP problem? Is it still one dimensional or is it kind of, it is 2 dimensional, right? Because you can see that there are 2 variables that are changing in all the different function calls. So let's say we have a function f and it returns an integer, which is total number of ways. And I need to pass here an index and remaining amount. Okay. Now, the first line of code, I can say if my remaining amount, this same thing can be copy pasted here. If the amount is 0, return 1. If amount is negative, return 0. And if I is negative, again return 0. Okay. Otherwise, what to do? Otherwise, if you are not at any of these termination conditions, it means you have to make the two calls. The first call is for leave and the second call is for take. So let's talk about it. See, you are currently at index I. So you are considering this area and you want to make this much amount. So if you are leaving this element, will your amount change? The answer is the amount won't change. So amount remains as it is if you are leaving it. But do you move back? Yes, we realize that whenever we leave, we move back. We move back. It's just the amount that does not change. So from I, you will move back to I minus 1. So the first call that you will make will be for this, and this corresponds to your leave transition. And then you need to have a take transition also. Can you tell me the variables for the take transition? Does the index change when you take something? Yes or no? The index doesn't change. So what changes? Amount changes. Yeah. And by how much your amount changes? It's natural to say that if you're taking array I, then the remaining amount will be amount minus array I. So why don't you write that? So the remaining amount will be amount minus array I, and your index stays the same. That's it. Return this thing. This is for your take transition. The code is over. That's it. Again, a classical recursion code which has certain base cases and one recurrence relation. Is that clear? How many of you find the code easy to understand now? Yes or no? Yeah, any questions so far? Okay, we'll move on now. So tell me, do you feel that again here there can be repeated subproblems, overlapping subproblems? If your net is lagging, can you please check your internet connection? I can see the speed at my end is perfectly okay. So it will definitely have overlapping subproblems again. For that, you will have to take a particular input. So let's say you have 1, 2, 4, and you have n equals to 10. How many of you can at least create a tree diagram for this? The way I have created here, can you create for this input? Yes or no? So please go back and create it. When you create, you will see that a particular problem which will repeat will be 1,6. So the point of me asking you to do this exercise is to convince yourself that overlapping subproblems will be there. So what to do if overlapping subproblems are there? How to tackle that? Memoization. So let's create a memoization array. Now think and say, what kind of memoization array will you need? 1D, 2D, 3D, which kind? 2D, very good. Two-dimensional array, because it's a two-dimensional problem. Now the next question is, what should be the size of it? What should be the dimension of this 2D array? Okay. See, at first dimension, you will have index I. Index, from where to where index varies? Can you tell me? Index will vary from 0 to m minus 1, where m is the size of our input array. So the first dimension will be of size m. And the second dimension is for amount. What is the maximum value of amount? It is n, and then over the function call, it goes on reducing. So you need a m cross n array, and you can initialize it to -1 something, and then you can write your memoization logic. So the first line of code you will have over here is memoization check. You will see if mem of I amount is not equals to -1, that means it is solved, so you can return this thing. Otherwise, you will make the two calls, you will add, and you will store this result in mem, and then you will return that mem. The memoization part is very easy. How many of you realize that the important thing is to write recursion, and then memoization is super easy to do? Do you realize that? Yes or no? Right? And that is what it is. So the real DP is memoization only. Okay. So DP is not tough. What is tough is your understanding of recursion. So that's the reason at Renaissance dashboard, if you take a look, we have given a lot of weightage to recursion and backtracking. And then you learn a lot of topics which are based on that, like trees, become superstar in recursion, and then only move on to something like DP. Cool, great. Do you see here that because the dimension of problem is high, so the space complexity is also high? I'll not talk about the case where n is 10 power 9 here, because in order to solve that, there are different ways to do that. So there you have to first look at the nature of input and figure out if the matrix could be sparse or not. And another way that you use to solve such problems is that is called as coordinate compression. So again, like that is not something which we'll venture into right now, but you can explore it if you're interested. Okay, cool. So, you know, a very interesting thing that you can do is once you go back from here, you can think of the bottom top approach. How many of you can already think of bottom top approach to this problem? Yes, no? So it is a very interesting thing to learn. So the second homework for you is go back today and learn about the bottom top approach of this same thing that I have discussed. You know, few more videos that you should be seeing after this class is knapsack problem. Please watch knapsack problem. And again, it is similar to this and a very, very frequently asked interview problem. Okay. I just wanted to cover one more problem, but it won't be covered in this much of time. So yeah, so I think it has been too much for today. If you have any questions to ask, do ask. Yeah, feel free to ask any place where you're feeling problem, any advice that you need in general. And then we'll meet tomorrow. We'll solve one DP problem and then we'll move on to some other topic. Questions, they're already there, no? They're already there on your dashboard. Are you guys able to find the questions on the dashboard, which we discuss here in the class? Yes or no? Yeah. If you're not able to find, then maybe please ask for it on the group. Your friends can help you with that. The one we cannot cover now. Oh, that is a very well-known problem. So that is called as edit distance. Another interview favorite question. You can read about edit distance. You can even watch the video and edit distance, and you can come back tomorrow and let me know. But you know, whatever we have discussed today is the most important part of DP. I mean, if you understand this thing in and out, it will be easy for you to understand almost all the videos, because for DP, what do you need to do? You first need to come up with a recursive code that, and for recursion, what do you need? Let's deep dive. For DP, you need recursion. For recursion, you need elements of choice, that how many choices we have at any point of time. And then you come up with an equation. Now, certain times in those equations, it might so happen that you end up getting duplicates. Like one of the expression that I wrote for this problem at the beginning had duplicates. So if it has duplicates, you have to discard that, come up with something else. When you come up with that something else, then you have to think about the termination condition. Then you write the recursive code, then you memorize it. So this is a well-defined approach for DP problems, which is never the case with any other topic. Any other topic can always have random set of problems where you have to think totally differently. But in case of DP, the steps are fixed. So if you are really, attentively listening to them, making notes of them, you'll find that over few months, it will be more and more intuitive to solve DP problems as compared to other topic problems. Yeah. Recordings, I think they are anyways shared always. You can check how long you can access dashboard and all that should be already available. Should we work on recursion on DP? Because DP is going on, so for now you should focus on DP. But then you should realize that if there is a part in DP which is hard for you, and if that part is recursion, then of course you should focus a lot on recursion. Yeah. Okay, guys, so that's it for today. Let's meet again tomorrow. Bye for today.